Hello, my fabulous chemistry students. Video number 5, average atomic mass. When we are done with this, we will be able to use our relative abundance knowledge to calculate the average atomic mass. Now, this particular periodic table is warped and skewed. It is designed to show you the relative amounts of each of these atoms. Okay, each element. Oxygen I see is the biggest. Carbon and hydrogen are probably the second biggest. In other words, the bulk of the planet is made up of carbon, hydrogen, and oxygen as far as percentage. Okay? That kind of information is actually useful. So, here is a quick thing. Weighted average. We know a little bit about weighted average. Weighted average is like, let me give you a good example. Your grades in school have a weighted average to them. Does it make sense that your grade in an elective class like art is weighted as much as, say, your math that's required? No, the math grade should be higher. As far as it determines more of your GPA, right? I mean, the math, the science, the English, the social studies, your core classes, they should determine more of it. I mean, your grade in gym should not trump. So the same goes with average atomic masses. Now, the periodic table, in the upper left-hand corner, we see in our tile, we see a mass, right? That mass is the average atomic mass, not just the mass of one particular isotope. It's all of them. Here's a little pictorial about how we take carbon-12 and carbon-13, use their relative abundance, how much there is of it on the planet. Most carbon is in the form of carbon-12, as you see, 99% of it. So I'm guessing my average is going to be closer to 12 than 13 just based on this whole 99% business and 1% business. Like the bulk of it's 99% is 12. The answer should be closer to 12. And what we're going to do is learn how to do this math so we can get there. So in calculating it, all I'm going to tell you about this real quick is that all percentages generically equal part over whole times 100. Well, in order for us to use a percentage in math now, I need to get rid of this 100 and bring it back into what we call decimal form. Okay? So let's say 99% divided by 100 equals 0.99. The thing that you don't want to get tripped up on is 4% divided by 100 is really 0.04. Okay? So where those zeros are is going to play a major key in our calculation. So here it's broken down for you. You'll see that the percent carbon at 12, I get 12 times the decimal. So this is already divided by 100. And again here, when I divide this 1.11 by 100, I get 0.011. So you need to be able to do that without any issues. I take my numbers, I add them together. That's pretty much in a bulk how we do it. So let's try our own. Okay, I'm going to do red for boron 10. I'm going to divide this by 100 right off the bat and go 0.199. And I'm also going to, wait, let me switch colors, Mr. Milks. Divide it by 100. This is going to equal 0.801. Now I'm in decimal form I can use. I have my masses that I can use. So let's start plugging these numbers in. 10.013 times 0.199 equals a number. I'm going to go ahead and keep setting it up before I calculate. 11.0093 times 0.801 is going to equal. Now let me just calculate these right through. Ready? I see 10.013 times 0.199 equals 1.992587. A little bit of calculator barf, but we keep it for now. I want to take care of that business at the end. Okay, yes, Mr. Milks, we need to keep the calculator barf just for a little bit. 8.818443. Now I need to add these boys back up. Add that to 1.992587. And what do we get? We get 10.8110363. And I see that I had 4 numbers after my decimal place and 4 numbers after my decimal place because there's a 0 there actually. So I got to go 4 numbers after my decimal place. 10.8110 or 10.811. Average atomic mass for boron based on the relative abundance. And that, you know what, it makes sense that if 80% of it is boron 11, shouldn't my answer be closer to 11 than 10? And it does. Beautiful. Next example. Uh-oh, they didn't give me the masses. Or did they? Well, in our notation, this is the number of protons, this is the mass. So I have a mass of 1, 99%. Let me divide that by 100 right off the bat to get 0.99. That's good. And then I have 2, and divide this by 100, and I get 1, 2, 0.006. And this mass is 3. Divide this one by 100, and I get 0.004. 2, yeah, 0.004. So now I can start adding or multiplying these things in. I'm going to take my mass of 1 times my relative abundance, and 1 times 0.99, I don't even need a calculator for that, 0.99, okay, good. Now I'm going to bring my 2 down, my mass, multiply it by my relative abundance, 0.0006, that I do need a calculator for, 2 times 0.006, 0.012. I'm going to bring my third mass, multiply it by its relative abundance, 3 times 0.004, I get 0.012. Now I need to add all these together, and I get, add 0.12 to it, add 0.99 to it, I get 1.014 for my relative mass of this particular hydrogen. Okay, good. Uh-oh, challenge practice. Chlorine has a naturally occurring isotope of, all right, for Cl35, it's almost 35. For Cl37, it's almost 37. If the atomic mass is this, what is the percent abundance? Okay, I'm going to set this up a little bit for you, and I'm going to give you a hint, and I'm going to see who can and who can't do this. Cl35 actually has a mass of 34.9689, and Cl37 actually has a mass of 36.9659. Now, what we don't know is this number that goes here. But I do know when I add them up, it comes, the answers, I get 35.4527. Okay? And I know that I'm going to take the relative abundances and I'm going to divide it by 100 to get to a decimal, right? Well, let's say if this one is going to be y, I'm going to color code these right so we can keep it straight, and this one's going to be x. I know if I take x plus y, I'm going to equal 1.0. That's how both of these guys get into decimals. So if I subtract, let's say I solve for x, right? X is going to equal, well, you know what? Let's solve for y because it's just easier. If I solve for y, then I can plug it back in. If I solve for y, I have to subtract x from both sides, so it's going to be 1 minus x, correct? Well, I see I have a y up here. So if I plug this value in for y, I will get x on top and 1 minus x down here. Now I can get rid of the y. There's a hint. So I'm going to take this number times x, this number times 1 minus x, add those two figures together, and I'll get this. Now I just need to solve for x. Once I have x, I can go back and solve for y. Let's see who can do that. So a little bit of notes and we're done. The mass number, the mass of one isotope of a given element. That's the mass number. But what's in your periodic table is the atomic mass, or the average mass of all the isotopes of a given element, how they naturally occur in the world. So we take some people have taken a lot of data to determine what those relative abundances are. We are going to need to be able to do the math to get to average atomic mass. So now we know what natural abundance is. It's the percentage of each element on the planet. We know how we can use it to calculate the average atomic mass. This is going to take some practice, and we will see questions on this, I promise, every year. Good night and happy studying.